Okay, can you see my screen?
Yeah, we can. So please start.
Thank you very much. Thank you for the introduction, Professor Nakata. And I'm Koji Hashimoto. I'm in Kyoto. And actually, in this Extreme Universe collaboration, I'm in the team of led by Professor Izuka as a kind of associate member. So I'm at really the edge of this Extreme Universe collaboration, but I really look forward to this Extreme Universe collaboration since I joined. And I'd like to thank all of you for giving me this chance to talk about the topic on chaos and holography, which I have been working on quite many years. And of course, as you already know, chaos have played a quite important role in ADS-50 correspondence. And well, in my opinion, I think it's still vague how this chaotic understanding of the universe and quantum information are related with each other. And I cannot talk about that too much since I haven't worked quite deeply into that direction, but I have worked on some novel aspects of chaotic features in holography, so I'd like to report on it. So I divided my talk into two parts. The first part is completely a review. I just want to explain the definition of quantum chaos and the subtlety about that, and also how black hole can be seen as a chaotic object, and then how ADS-CFT may relate these two things. And in the second half, I'd like to talk about some recent progress on quantum chaos in view of ADS-CFT correspondence. So mainly the last section will be devoted to my very recent work done with Murata-san and Tanahashi-san. They are in this Extreme Universe collaboration, and my graduate student Watanabe-kun. And also I'd like to mention my brilliant collaborators, Akutagawa-san, Dr. Fu, Professor Kim, Miyazaki-san, Murata-san, Oto-san, Sasaki-san, Tanahashi-san, Yoshida-san, Yoshii-san, Watanabe-san. So all of their effort to find the new things in quantum chaos and holography reached to this stage. Thank you. So before I start my talk, I'd like to briefly mention how our stage of ADS-CFT correspondence reached this height. It's been already 24 years since ADS-CFT was born. Let me look back briefly. Podzinsky found D-brain in 1995. Sorry, D-brain was discovered much earlier, and in 1995, he considered effective field theory on the D-brain, and we had a way to treat supersymmetric QFT in string theory. And then in 1998, 24 years ago, ADS-CFT correspondence was claimed by Madasina. And later on, we have a lot of developments about a kind of application or deeper understanding of space-time, starting with Sakai's Imoto, I would say, about how the QCD, from which string theory was born, is now related to ADS-CFT correspondence. And this is a nice understanding of how string theory should be equal to gauge theories. And then, as all of you know, Ryu Takayanagi claim about the quantum entanglement understood as a surface area in ADS. And then I skip many detailed advancement in ADS-CFT, but in 2020, chaos picture was presented by Kilev. Well, I would say that, of course, there are many others like shock waves, and details will be explained later. So let me just tell you only some names. And then at the same time, 2014, the quantum computational complexity was claimed to be equal to describing inside of the black hole horizons. And then very recently in 2019, we have island formula by Pennington, and how information recovery and quantum information can be related to wormhole summation in quantum gravity. And through all of these excitement, we still lack how ADS-CFT works, how emergent space-time actually emerges from information or quantum field theory. So one of the goals of this ADS-CFT correspondence research is to answer this question: what kind of quantum field theory allows a gravity dual? So suppose you have your favorite quantum mechanics or quantum field theory or quantum information system, then you can ask whether this system has a gravity description or not. To answer this question, actually, it's very difficult. And so far, I think there is no kind of universal understanding of how to answer this question. And to answer this question or to tackle this kind of question, there are many ways. As you can see below, you can use entanglement entropy and the property of entanglement entropy to actually discriminate whether the quantum field theory has a gravity dual or not. Or you can also use these other criteria. Well, I think I would say that entanglement entropy and also properties of spectra or correlators, those are most kind of advanced to answer this question. But rather, for example, this complexity or chaos or island formula, these are not well studied so far to tackle this kind of question. Of course, these are really much have been studied in detail in both quantum field theory side and the gravity side. But the question is, we want to answer this kind of question, and to that direction, still we lack intrinsic understanding of how these things works. So today, since I have been working on chaos quite much, I'd like to concentrate on this picture of equating horizon equal to chaos, and then explore this kind of question and how we can answer this question. Of course, I don't have a good answer to this question still, but we can have some progress using this notion of horizon equal to chaos. Before starting this detailed discussion about horizon equal to chaos, in fact, there was a very interesting paper by Stephen Hawking in 2014. So this paper is a kind of, it's not really a poem, but it's like a poem, since this paper doesn't have many equations. It doesn't explain in a logical sense by equations, but I thought that this Hawking's paper was quite interesting. So as you can see in this abstract, he said that the collapse to form a black hole will in general be chaotic. Thus, like weather forecasting on Earth, information will effectively be lost, although there would be no loss of unitarity. Yeah, so this is a quite generic statement, and I don't actually know what exactly Hawking meant to say here, but you can see the sense of it. The black hole is there and it's fast scramble, so information is effectively lost, although it's not lost. But the goal of our research is to precisely explain this statement by equations. Okay. So my talk was divided into 4 parts. First section and second section is a review, and third section and fourth section. So these are kind of explaining our work, which was done with my collaborators. But first, in section 1, I'd like to define quantum chaos. And in fact, there is a subtlety there, and I'd like to mention that. This subtlety actually becomes important in section 3. There are 2 definitions of quantum chaos. And we use both, so we use the word chaos in both meanings, and that's actually creates some complications. And in section 2, I would like to review how the black hole horizons behaves the nest of chaos, and it's universal. In section 3, I'd like to propose a way to look for a black hole like quantum mechanics. If I want to actually create a gravitational system on a tabletop experiment, then we use ADS-CFT and we look for some quantum mechanics which can be realized on tabletop, and how we can find that kind of quantum mechanics. That's the question. And I failed. Of course, SYK is one of the successful examples, and I tried to find a similar system, but I failed. And here I'd like to explain the difficulty and also the possibility. And in section 4, since I failed in section 3, I changed my mind and I tried to find another way to attack this kind of question. And I reached a conjecture. In fact, this conjecture was announced already 5 years ago as a footnote of my paper, which was published already. But I missed the importance of that footnote, and 5 years passed, and then we formulated this conjecture in a concise way. So section 4 is for that, and I hope that, so this is just a conjecture, but I hope that this may help how space-time may be emergent, we will know, and how, yeah, chaos may help the mystery to reveal, may help to reveal the mystery of extreme universe. Okay, so let me start with section 1. I have 4 slides. First, I'd like to explain what is classical chaos, and this is an example. And there is a standard question, there could be no quantum chaos in quantum systems. And the answer to this question is that, in fact, we have 2 definitions of quantum chaos. So let me start. So what is classical chaos? So if you look at Wikipedia, then this is a definition. It's a non-periodic bounded orbit sensitive to initial conditions in nonlinear deterministic dynamical systems. So it could be just a Hamiltonian system. It could be non-Hamiltonian system. But in fact, if it's a deterministic nonlinear dynamical systems and the orbits are bounded, then normally it's classically chaotic. So how we can actually see the sensitivity to the initial condition? So if you look at the Poincare section, which is defined as follows. So this is a phase space, and this is a motion in the phase space. Consider, for example, a particle in 2-dimensional or 3-dimensional system, then the phase space is 4-dimensional or 6-dimensional. And then you consider a section, and then consider the cross-section of this orbit with this sheet. And then if these points are aligned on a circle regular orbit, then you would say that this is a regular system. But if these points are scattered, then you would say that this is a classically chaotic. So this is a very famous way to diagnose whether this system is chaotic or not. And how about sensitivity to the initial conditions? This is measured by a so-called Lyapunov exponent, lambda. Suppose you consider an orbit in phase space, and then consider a very small slight change of the initial condition to here. Then the phase space motion goes like this. And if these 2 motions are displaced by an exponentially growing function, like exponential of lambda t, where lambda is positive, then you can say that this is quite sensitive to the initial condition. So it's chaotic. So there is a way to numerically measure this Lyapunov exponent for classically dynamical systems. And then if this lambda is positive, then you would say that the system is chaotic. The famous example is stadium billiard. So you put a particle in a stadium, which is defined by rectangular shape plus circle. and then the ball bounces at the wall of this period. If you put plot this bronchial section, then you can say that it's scattered. If you measure the Lyapunov exponent, I'm sorry, this is lambda, then you can say that it's positive. So this is the parameter parameterizing the shape of this period. And then this is the Lyapunov exponent. Then it turns out that it's positive. So this is chaotic. So far it's okay. So the chaos has started by the work by Lawrence about the prediction of weather forecast. And now it grows quite a big field of research, and classical chaos is quite well understood in physics and mathematics. And since we are a quantum physicist, we want to ask this kind of question in quantum mechanics. But you would say that there should be no quantum chaos in quantum systems. The reason, you can come up with many reasons. The popular reasons as follows. Reason one, a Schrödinger equation is linear, but a classically chaotic system needs nonlinear system. That's true. Reason two, I said that the initial condition sensitivity is important for chaos as a definition. But in quantum systems, if you want to place two particles very close to each other, since there is a uncertainty relation, it's impossible. So infinitesimal change in initial condition does not exist in quantum systems. Sure, it's true. So while in quantum systems, it's very kind of obscure how to define chaos according to this definition of classical chaos. So what people did is as follows. First, you prepare classically chaotic system and then quantize it. Then you call it quantum chaos because it was classically chaotic and you quantize it. So it's called quantum chaotic. And in fact, if you look at the quantum chaotic systems from this definition quite in detail, then you can find that in fact the quantum energy level, which are of course quantized, the level spacings follow a very particular statistical law, that is Wigner's distribution. So here on your left side, this is the atomic spectra of lithium in the electric field. If you increase the electric field, then this is the spectra, which is the symmetry is broken by electric field, and then it reaches some random kind of distribution. The spacing, if you look at spacings, then they look repelling each other. And on your right-hand side, this is an interesting paper by Panzayas in 2000. It's about the hadron spectra spacings. QCD is quite complicated system, and we would say that it's chaotic. The reason he mentioned is that if you look at hadron spectra spacings, then this is the spacing, this is statistics, and then it follows this Wigner distribution. So in this sense, of course, you cannot take a classical limit of QCD, but if you think that this is kind of classically chaotic system and quantized, then it should follow this Wigner's distribution. And in fact, if you look at the experimental data of hadrons, then you have Wigner's distribution. So there are two definitions of quantum chaos. The first definition is what I mentioned. So first, you prepare classically chaotic system. The definition is clear, and then you quantize it. Then you name it quantum chaotic. And I may call this actually a quantum chaos. And the following second definition, I don't want to call it chaos because it's different from classically chaotic notion. For this first definition, in fact, there is a very beautiful paper by Stefan Heusler and his collaborators. It's about the proof of this statement. The energy level spacings follow Wigner's distribution if you quantize the system which was classically chaotic. So there is a proof of the equivalence between the classically chaotic system, and once you quantize the energy level spacings follow Wigner's distribution. So the people were right. So if you look at energy level spacings and if it follows Wigner's distribution, then you can actually kind of show that in the classical limit, it shows chaos. So what is this definition 2? And I think this definition is kind of more popular in area safety correspondence and recent research. It is the exponential growth of out-of-time order correlator. So consider, for example, a quantum mechanics, one-dimensional quantum mechanics. And then in the Heisenberg picture, you prepare x of t, p of 0, x of t, p of 0, averaged over some quantum state. And then if this grows exponentially in time t, then you would call this quantum chaotic. This is a kind of popular way of defining quantum chaos in quantum systems since it was used by Kitaev in 2014. And some people call this scrambling to distinguish this definition and that definition carefully. But this scrambling, the word scrambling has been used in kind of different contexts. So it's still kind of confusing. Yeah, so this confusion between these two things, I will revisit this in section 3. But anyway, this is the definition of quantum chaos, the definition 2. Lambda, which is positive, appearing in this out-of-time order OTO correlator, is called quantum Lyapunov exponent. The reason why this is related to classical chaos is as follows. If you replace this XP product by a commutator, then in the classical limit, this commutator is replaced by this Poisson bracket. And so this is replaced by this in the semi-classical limit, and this is nothing but this picture. So it's exponential. If it's exponentially growing, then it's classically chaotic. So this notion of ODO is a kind of quantum replacement of the classical chaotic definition. So both of these definitions look okay, but since our goal is to find a quantum system which allows a gravity dual description, we need to be careful about these two things. So this is the end of section 1. I explained classical chaos and its definition. Example is the stadium media. I explained intuitive reason why we expect no quantum chaos in quantum system. But in the semi-classical limit, in fact, we have two definitions of quantum chaos. So let me go to section 2. So here in section 2, I'd like to review a black hole horizon and its chaotic nature. I have 4 slides for section 2. The first, historically, in fact, chaotic motion around black hole has been known for astrophysicists, but there was a problem. And in section 2, there is a great advancement in area CFT, showing that Lyapunov is in fact the Hawking temperature of black hole. And later on, Marlis Nashenka and Stanford discovered this quantum Lyapunov upper bound, and saturation of that was important to diagnose area CFT correspondence. And finally, in section 2.4, I'd like to mention that chaotic motion near horizon is a kind of universal. So let me start with section 2.1. So 1 slide for each. If you look back 1996 paper by Suzuki and Maeda, in fact, they found that a motion of spinning particle going around curved black hole was chaotic. So this is the Poincare section of this particle which is moving around curved black hole. And if the spin of this particle is large, then they found that Poincare section has a scattered plot. So it's classically chaotic. But in fact, there are 2 problems about that. So we want to use this kind of fact to diagnose black holes, nature of the black hole. But the motion actually is far from horizon. So the motion of this particle is not near the horizon, but it's far from the black hole horizon. It's above the so-called radius of photon sphere. So it's far from horizon. So how we can find the universal feature of black hole out of this chaotic property? That's the question. And also, second reason is that the geodesic motion around Schwarzschild curve is in fact integrable. So if you put a spinless particle, then it's integrable. So there is no chaos. So how the chaotic nature of black hole can be actually deduced from this motion of a particle going around the black hole is still mysterious. So we need some other kind of idea to look at the black hole more precisely. The great turning point was made by Sekino and Susskind black hole, the fastest scramble conjecture. Here they put a kind of charged particle and they put near the horizon, and then the particle falls down to the horizon. And an asymptotic observer looking at that, actually the black hole becomes gradually charged, and then the flux emanating from black hole becomes uniform, and then the time scale of this uniforming process is fastest for the black hole. So that's why Sekino and Susskind argued that the black hole is the fastest scrambler. And later on, Schenker and Stanford showed that actually there is a shock wave delay once you shoot a shock wave into the black hole and see how the particle, which was very near, moving very near the horizon, comes out to the ADS boundary, can be seen as a chaotic kind of understanding of this black hole. And Lyapunov measured was equal to the Hawking temperature of the black hole. So this shows that this black hole system has a universal chaotic nature. And the explanation of this shockwave delay was using this out-of-time order correlator, and it's kind of complicated. So here I use a beautiful work by Armeni Podzinsky and also Engrusoy, Martens, and Perlin in 2016 about the 2D dilaton gravity, which was supposed to be due to SYK. So this is a Penrose diagram, and here you have a black hole horizon, and consider a particle which reaches at the ADS boundary at time t2. And then consider shooting in another particle of energy delta E at time t1 going into the horizon. Once this particle goes into the horizon, then black holes becomes a little bit fatter. And then this location of the horizon, because of the inclusion of absorption of this T1 particle, the location of the horizon becomes moves from this blue dashed line to red dashed line. And because of this, this time T2 is kind of delayed. So it's a very intuitive picture. So particle going near the horizon, of course, suffers from a redshift. And once the black hole becomes a little bit fat, then the motion of the particle becomes effectively closer to the horizon. So it is affected by this redshift factor for longer time. So it becomes a time delay. And the computation of time delay in 2D gravity can be easily done. And it's proportional to this delta E, which is the energy of the first particle. But the point is that the effect comes as an exponential factor as a function of time. And the coefficient is 2 pi times Hawking temperature. So this means that the Lyapunov exponent of this system is Hawking temperature times 2 pi. So this is a gravity understanding of how a chaotic Lyapunov exponent can come out from the universality of horizon. picture. And suggested by these things, Madison, Shenkan, and Stanford actually proposed a quantum Lyapunov upper bound for thermal ODOC correlators for a quantum large N system. The Lyapunov exponent in any large N quantum system should obey this inequality. The upper bound is given by 2 pi times temperature divided by h bar. And this was, of course, suggested from AD safety correspondence as before. And Madasuna, Shenkan, and Stanford formally gave a proof of this bound by assuming several things. Yeah, and those assumptions are quite natural. So this upper bound, we would say that it's proven. But we need to require large N and quantum because h bar. So in the right hand side, this is in fact divided by h bar. And since I put h bar equal to 1 here in this equation, h bar is missing, but h bar is in the denominator. And Kita showed that SYK model saturates this bound. In this talk, I don't talk about SYK model, but for those who are not familiar with that, I just wrote the definition. And this quite interesting model, which includes disordered summation, is wonderfully solvable at large N and stone coupling. And you can compute out of time order correlator for this model. And then you can actually find the Lyapunov exponent, which is equal to 2 pi t over h bar. So this means that since Lyapunov exponent from this shock wave computation always shows that it's 2 pi t, and it's the upper bound from this inequality. So we say that quantum system which has a gravity dual need to saturate this bound. So this is the way how to discriminate quantum mechanical system which has a gravity dual and quantum mechanical system which doesn't have a gravity dual. If you compute ODOC at finite temperature, and then you can, if you read off this quantum Lyapunov exponent, and then if it is equal to 2 pi t over h bar, then the system has a gravity dual. One comment is that this chaotic motion, chaotic nature of black hole horizon given by shock wave can be actually seen for the case of for the case of motion of a particle near horizon. Historically, I said that it was the particle was moving very far from the horizon, so it's difficult. Yes, that's true. But if we include some other kind of artificial potential to make it very close to the horizon, then in fact, the Lyapunov exponent is always equal to the Hawking temperature, you can actually show. So this is a particle, this is a black hole, and here is the horizon. There is a gravitational force, but I implement another artificial potential, which could be electromagnetic potential or other potential, so that this does not fall into the horizon immediately. Then this is the particle motion near the horizon, and this is the artificial potential. And if you expand this potential, the total Hamiltonian, around this instability point, then the curvature, the curvature around here is shown to be always equal to 1 over 2 pi t squared. And once you have this kind of inverted harmonic oscillator potential like this, then there is an exponential growth of a particle motion around here. And it is dictated by this frequency parameter. So 2 pi times Hawking temperature is always the Lyapunov exponent of the black hole. So here is the end of the section 2. I finished the review. So chaotic motion was known to be known in the history around black hole, but it has it did not probe the black hole horizon. And using shock wave, in fact, Lyapunov exponent is shown to be equal to Hawking temperature. And Mada-Sanashenko and Stanford showed the quantum Lyapunov upper bound. And if you put the particle very close to the horizon, then in fact, you can see this nature by particle motion. So this is the end of the review part. And now I'd like to go into section 3 and 4. In section 3, I'd like to propose a protocol to find a black hole-like quantum mechanics to be a hope for putting a tabletop experiment of black hole in condensed matter physics. And then I failed. And so in section 2, I'd like to propose a new approach. So everything is about this slide, which I showed at the beginning of my talk. So I'd like to use this horizon equal to chaos, this equality to diagnose the ADCFT correspondence. And you have already seen that protocol is to look for a quantum system whose quantum Lyapunov exponent is equal to 2 pi times temperature divided by h bar. If you can find a quantum mechanics which saturate the Mada-Sanashenko-Stanford bound, then that's a candidate, a very good candidate, like SYK model, to have a gravity dual. Okay, so section 3, I have 6 slides. First, I'd like to mention that computing ODOC is in fact very difficult. If you have tried this, then you know that it's very, very difficult. And I will explain the reason why it's difficult to analytically compute it. So in that sense, Kitaev's computation was really a genius technology. And then I propose a protocol to how to look for black hole-like quantum mechanics. And here are some examples of quantum mechanics, like quantum billiards, harmonic oscillators, inverted harmonic oscillators. And finally, I reached a strange contradiction among scrambling and chaos. So I said that there are 2 definitions. And in fact, they are different. So we need to be careful about when we say chaos in quantum mechanics. So that's a kind of failure conclusion of mine in section 3. It's a kind of negative message, but yeah, I'd like to explain that. So from section 3.1, computing ODOC is difficult. So why difficult? So all of us know that N equal 4 supersymmetric Young-Mills theory has a gravity dual. Yes, it's the original theory claimed for ADS-50 correspondence. So why not computing ODOC for N equal 4 supersymmetric Young-Mills? If you can compute it, then of course this is a great check of how this diagnosis can work for discriminating holographic quantum mechanics. It's difficult. There are 3 reasons for that. First of all, the ADCFT correspondence was born from deep brain dynamics. And on deep brain, you have always gauge fields, and in particular, non-abelian gauge fields. And ADCFT works for strong coupling limits of those gauge theories. Okay, and the most popular gauge theory, which we know about, is QCD. But even for QCD, we don't have any good idea of ground state wave function. It's proven to be quite difficult since it's one of the problems in millennium programs in mathematics. And if you want to compute ODOC naively, then we need energy eigenstate wave function. But of course, it's unknown. So what do? We need some other technologies than the usual Hilbert space technologies for N equal 4 supersymmetric Young-Mills theory. And the second reason is that perturbation theory does not give long time behavior. So out of time autocorrelator, suppose you could compute it in perturbation theory. Yeah, that may be true if you do weak coupling expansion. But what we want to know about ODOC is the exponential growth of it, right? And nonlinearity gives that. The nonlinearity comes from the coupling constant. So if we do weak coupling expansion, then we cannot follow this exponential growth, right? So this is the kind of contradiction of what we want to do and what we have as a technology. And in fact, there is a nice paper by Stanford. It's a combination of ODLC of 5-4 matrix theory. He tried to do weak coupling expansion, but he sum up all the ladder diagrams by using some assumption about what kind of diagrams in Feynman diagram sum is necessary for ODLC, and these diagrams may not be necessary. And he used just a ladder diagram and then compute ODLC, and he showed that it could be exponentially diverging. But he assumed what kind of Feynman diagrams contribute to ODLC. And that assumption, I don't know how to prove it. So in this way, weak coupling expansion, you can use ladder summation, but you need to use those assumptions. And also, if you look at, for example, Iizuka-Polchinski model or Iizuka-Okuda-Polchinski model, then they have used in early days. This is a model for gravity picture. Mitchell, Polchinski, Rosenhaus, and Su computed ODLC by using Schwinger-Dyson equations for IP model and IOP model, and they showed that in fact ODLC doesn't grow exponentially for these models. So these models are kind of popular and famous for approaching gravitational picture from QFT side, but unfortunately it didn't give exponential growth of ODLC. So you may say that, of course, QFT allows path integral, so we can use it. But no, for out of time order correlator, you cannot use it because it's out of time order. Path integral scattering amplitude computation is equivalent to time order correlators. But now we are interested in out of time order. So how do we do that? It could be a generalization of Kildish formalism for finite temperature real-time formulation of QFT, but it's kind of difficult. So there are numerous number of reasons why ODLC is in fact difficult for example, the computation in gauge theories, which are really popular in ADS-CFT correspondence. SYK is not a gauge theory, and SYK allows quite interesting technologies to sum up all the diagrams in a certain limit. So it's quite carefully chosen theory to test this ADS-CFT correspondence. And of course, there are several arguments how to derive SYK model in the context of string compactification, but it's rather obscure how you can put it on the brains and you take a low energy limit. So general ADS-CFT correspondence does not allow an easy computation of ODLC. That's why, in fact, to look for black hole-like quantum mechanics in ADS-CFT correspondence is difficult. But at least I can try. Since ODLC for quantum mechanics is easy, gauge theory is difficult. Yeah, that's true. And SYK is quite finely tuned to compute ODLC. That's great. But I'm not genius. I'm not Kitaev. So I can try my way. So let's consider the simplest quantum mechanics like harmonic oscillator, and then compute ODLC and check whether it saturates the Maurer-Senashenka-Stanford bound. That's what we can do. So how to compute ODLC is as follows. Prepare your quantum mechanical Hamiltonian, and then solve for energy eigenstates. And then you calculate microcanonical out of time order correlator like this. So these are in Heisenberg picture operators. And then you compute the expectation value with this energy eigenstate. Then for this quantum mechanical system, you have this density of state. Then using this microcanonical ODOC, substitute this result to here, and then make an integration over energy with inverse temperature beta. Then you call it thermal ODOC. If this grows exponentially, then you can read off the Lyapunov exponent. So this is a log of this thermal ODOC divided by time t for t large, then you get this Lyapunov exponent. So following these 4 steps, in fact, you can compute explicitly for a given quantum mechanics, at least numerically. So let me show you some result on quantum mechanics. So here, for example, harmonic oscillator. So this is a harmonic oscillator. Computation of ODOC can be done exactly, analytically, and it gives cosine squares of omega t. It's periodic, so there is no exponential growth, meaning no scrub, following definition 2. What about particle in box? It does not grow exponentially, so this is log scale, thermal ODOC as a function of time. The circle billiard, this is classically integrable. There is no exponential growth. Stadium billiard, this is classically chaotic. Unfortunately, there is no exponential growth. So you can carefully look at this part, and then, well, this part may be exponentially growing, but there is no way to distinguish. So unfortunately, there is no exponential growth. So the lesson from here is that stadium billiard is classically chaotic, but in quantum mechanical systems, it does not give you the exponential growth of ODOC. The next example is coupled harmonic oscillator. So this is the Hamiltonian. X and Y, those are harmonic oscillators. They are coupled. This Hamiltonian is interesting because it's an essential part of a BFSS matrix model, which is a one-dimensional quantum mechanical model, which has the gravity dual. Since you need to take Large limit for BFSS matrix model, it's difficult numerically. So I used only 2 components among infinite components and compute the thermal ODOC. If you look at the classical Poincare sections, then it's scatter plot, so classically chaotic. And then you can actually compute the out of time order correlator numerically. So this is the log plot as a function of time. You can see that it's exponentially growing around here. Yeah, I know that it's subtle to actually claim that this is exponential behavior, but there are several criteria to actually say that whether this is exponentially growing or not, is correct or not. And the final example is this inverted harmonic oscillator. So this is the potential. Since this is a one-dimensional system, classically, there is no classical chaos. It's proven. It's called Poincare-Bendixson theorem. One-dimensional Hamiltonian system does not give any classical chaos. So let me quantize it. These are quantum energy levels, and to these red lines are quantum energy levels which is close to this top of the potential, the inverted harmonic oscillator. And if you choose these things, and if you actually fine-tune the temperature around here, then the out-of-time order correlator grows exponentially. So this example says that although classically it's not chaotic, there is a growth, exponential growth in out-of-time order correlator. So here is a summary. Harmonic oscillator, billiard, coupled harmonic oscillator, inverted harmonic oscillator. There are 2 definitions. The definition 1 is that you bring classically chaotic system and quantize it. Definition 2 is the exponential growth of out-of-time order correlator. Definition 1 is easy. Classical billiard is chaotic. coupled harmonic oscillator was chaotic classically. But these two things are regular. Then now we quantize it. Exponential growth was seen for these two things, but it has not been seen in these things. So there is a distinction between these two. All of the possible 4 cases are shown here for quite easy cases. So what do? Well, for ADS-CFT correspondence, the lesson is that we shouldn't actually care about whether the original system, classical system, was chaotic or not. Rather, we need to look at the scrambling, the exponential growth of ODOC. And in fact, you can see that there is a growth here. And so this is more important for us. This was not important for us. And so that's the lesson. So here is a summary. We looked at many quantum mechanical systems. We can actually compute ODOC for easy systems. And then we can actually look for the black hole-like quantum mechanics by computing ODOC and whether it shows the saturation of the Malder-Snarchenko-Stanford bound. What I meant by failure, my failure, is that although I tried many quantum systems, I still don't get a quite nice system which saturates the Malder-Snarchenko-Stanford bound. One reason of the difficulty is that, in fact, finite temperature computation is difficult. The energy eigenstate computation was easier. So the conversion from microcanonical ODOC to canonical ODOC was kind of difficult. So in final section, I have already, I have 5 minutes or so. I'm sorry about that. So let me come to the conjecture. I have 5 slides. So this conjecture was actually came out of the difficulty of computation of ODOC. So let me explain the conjecture. And this conjecture was quite universal. It's more universal compared to Malder-Snarchenko-Stanford conjecture about classical chaos bound. For example, general Villiers and general 2D mechanics, classical mechanics satisfy the bound. And this new bound, the saturation of the new bound is necessary for black holes. And finally, I talk about some dreams. So this is the 4 steps to compute the thermal ODOC. But here, in the 3rd step, there is an integral of this microcanonical ODOC over energy. And numerically, you can do it for well-defined system, but I noticed that this is not always possible. The reason is that if this microcanonical Lyapunov exponent, which is hidden here, grows faster than linearly in energy, then since this is the energy integral, this integral diverges. So you cannot go to canonical ensemble. That's strange. Normally, we understand that any given system, you can go to finite temperature. Yeah, I believe it's true. However, if this microcanonical ODOC is growing in time exponentially, and that it's Lyapunov is a function of energy, grows faster than linearly energy, then this integral diverges. So you cannot go to canonical. So this gives you a new bound. We call chaos energy bound. If Lyapunov is proportional to energy to some power C at the high energy limit, then this C needs to be equal to 1 or smaller than 1. If this is violated, then you cannot go to finite temperature system. As you know, ODOC was proposed very recently, and before that, we rather take a canonical limit quite naturally, but since ODOC may behave very strangely, we need to require the consistency of canonical ensemble in this way. And this consistency gives you this bound. So this is a conjecture. Lyapunov does not grow faster than linearly in energy, the high energy limit. And this conjecture needs to be applied to any physical system, quantum or classical, or large n or finite n. This needs to be true. And in fact, if you look at classical systems, very famous classical chaotic systems like double pendulum, HH system, particle in black hole geometry, blah, blah, blah. All of these things in the high energy limit seems to satisfy this bound. So it's interesting. I didn't expect that the chaotic nature of any physical system has a bound. Well, you need to be careful. The chaos bound by Madison, Shenkan, Stanford, that's for quantum system and large n system. And here, this conjecture is not only for quantum, but also to classical, and not only for large n, but also finite. I have non-trivial examples to explain this bound for general billiards and also 2D mechanics, but because I don't have much time, I will skip it. So interestingly, all of these examples satisfy the chaos energy bound. So let me briefly tell you that this is almost the last slide. So this is the chaos energy bound. Lyapunov, the C is smaller than 1. So this is the famous chaos bound by Madison, Shenkan, Stanford, how these are related with each other. Suppose this chaos energy bound is saturated like this. So C is equal to 1. So Lyapunov is proportional to energy. Then normally, if you take large n limit, then the energy is proportional to temperature. This is true only in large n limit. In a large n limit, this energy integral can be replaced by saddle point, and this is a saddle point. So this Lyapunov in energy picture becomes Lyapunov in temperature picture. So in large n, this saturation means this one, and this one is a necessary condition to saturate this one. So in Madison, Shenkan, Stanford bound, the precise coefficient is given. But here we discuss only the temperature dependence, and this linearity is hidden in this exponency. So that's the relation between chaos energy bound and the Madison, Shenkan, Stanford bound. So we would say that to saturate this bound, this needs to be true for quantum and large n systems. And this saturation is given by this saturation. So this bound needs to be saturated too. So it's a kind of necessary condition. Okay, so this is the final message.
Can I ask a question?
Please.
So for this, so are you assuming energy and the temperature is proportional to each other?
No, I didn't assume that.
Because I thought that U equal gamma T.
That's right. So here, what I assumed is standard large n limit and a standard kind of density of states, which is not the kind of exponential, but the power. And if you assume these two, then you can actually prove this for, you can prove the relation between canonical correlator and the microcanonical correlator. You can just replace energy by gamma times T by saddle point approximation. Did I answer your question?
So that depends on density of state.
That's right.
But in quantum, for example, for conformal field theory, energy is proportional to temperature to some power. But maybe you are looking different energy. So energy for each particle?
No, energy, the total energy.
Total energy, yes. That's case, then maybe this power can be changed, or I just want, or maybe you're choosing different density of state in that case.
Let's see. So let's see. So here, if I go back to this equation. So what I did is, so let me explain what I did, and then you may find where is the discrepancy comes from. So here, assuming that this density of state is a power of energy, the total energy, then exponential minus beta E, this is the standard Boltzmann factor. And then in the energy integral, assuming that this one and this one gives you a saddle point, then temperature is always given by energy, the total energy. So that's the saddle point. And so you need to substitute that value, the temperature here. So that's the, I think that's a standard way to explain how in the large energy system, the energy is always given by the temperature. But
But yeah, also we have also volume and other factors.
Yeah. So, so normally in CFD, it's energy density. Right? Yeah.
Maybe find because finite volume or.
Yeah, I think the volume needs to be carefully taken. So since this E is in the Boltzmann factor is always the total energy, right? So
let's see. Yeah, let me discuss.
Another
question is, I think in your first part, you also mentioned this. I mean, in chaos, this spectrum is very important, and you have a very nice explanation of this Wigner distribution. Or is that kind of distribution is relevant in this calculation? For rho E, we might have such a distribution.
Yes.
But maybe you are talking some saddle point approximation, maybe not so important, or I'm just curious about the relation between first definition and your second definition.
That's interesting. So in fact, I haven't thought about that precise relation between. So here it seems that, so it looks that they are, so that's different. So here, what we need to assume is the high energy behavior of this density of states, and that's it. So on the Wigner distribution is only for this energy level spacings and its statistics. Yeah, but I'm afraid that if you think about conformal field theories or some kind of non-particle like systems.
Yes.
Yeah. This definition of computation of density of states and this statistics may be related. I don't know.
Can I ask something?
Yeah, please.
Yeah, I thought that this conditional energy levels are kind of the definition or diagonals of chaos at the quantum level, and this autark is just the scrambling. I mean, it's just because chaotic and scrambling is different properties, right? Scrambling is how fast you can go at the quantum level. Forget about classical. And then a chaotic is a chaotic dynamics. Say energy density is really, distributed, say randomly. I mean, it's Wigner distribution and so on.
Yeah.
So there may be some relation, or like if one is satisfied, it's likely to be the other is also satisfied, but the definition is different and no reason that they are same.
I agree. Yeah, I agree.
Yeah. And you're looking into scrambling behavior in that sense. Of course, it's worrying, the terminology.
Yeah, the terminology is kind of, really confused all of us. For example, this inverted harmonic oscillator, it's not chaotic classically. But if you look at the top of the potential hill, then it can generate exponential growth somehow. So if you,
quantum mechanically, it's scrambling, as you say, yes. Autark satisfy this exponential behavior.
Yes.
But classically, it's a different distance leads to exponentially because it's inverted.
Right.
Okay, so in that sense, same with the classically. Now it's a classical, it's not chaos, but in the quantum mechanically, also energy levels are not random. It's just a very simple thing, just inverted. It's the same again in classical and quantum.
Yeah, so I think that's a good question. And when we talked about this exponential growth of this sensitivity to the initial condition, yes, this is true. But in Hamiltonian systems, it's known that in phase space, if there is an expanding direction with a positive Lyapunov exponent, then the diagonal component will be shrinking like this. So this kind of, so phase space volume is of course maintained in time
sure.
evolution. So once one direction is elongated, the other direction is shrunken. So this kind of understanding needs to be implemented for out of time order correlator understanding. Since out of time order correlator look at only one direction, and if one direction exponential grows, then can we say that it's chaotic? No.
Yeah, I'm saying, yeah, that's why it's chaos and scrambling is a different thing.
Yeah, thank you for the point. Thank you for the questions. And so let me finish with just one slide. Just one slide. Sorry about that. Here is the last slide. So so far we have looked at chaos and how this saturating the upper bound of Lyapunov exponent may distinguish or discriminate holographic quantum mechanics. And this is an interesting book by Frogat and Nielsen, The Origin of Symmetries. In figure 1.1, they have this picture. Start with low energy, non-relativistic, the standard model, ground unification, quantum gravity, string theory. And then at high energy, maybe chaos may be important to choose these dynamics from many possible dynamics. So I think this is a kind of dream picture by Frogat and Nielsen. But let me seriously think about this thing. The Lyapunov exponent in classical mechanics is known to be equal to Kolmogorov-Sinai entropy production rate. And so suppose there is a bound on Lyapunov exponent, then saturation means that it's the fastest entropy production system at high energy. Okay, and using this fact, quantum field theory, which may saturate the chaos energy bound, is the highest or fastest entropy production system. So if you use entropic principle, then this system needs to be selected as a theory of the extreme universe. What do you think? So why do we have this upper bound? That's an interesting question. For example, in the paper by Parmuta, he discussed that the gravity gives you the upper bound. If you allow higher spin fields, then this bound may be violated. So it's related to unitarity in space-time. So there are many related kind of notions here. And here we have this chaos energy bound. Suppose it's saturated, then what happens? Then it gives you the fastest entropy production in the sense of Kolmogorov and Sinai. Of course, the largest entropy may dominate the universe. So this could be the selection principle. I may say, I don't know what you say, but this is the end of my talk. So finally, today, thank you for listening to my talks. I'm sorry that I extended my time. Chaos and holography, it's interesting, and you know how to compute ODOC. So let's discuss. Thank you very much.
Thank you very much for a nice talk. Reaction, clapping hands. Yes, thank you very much. Okay, so it's time for questions. So if you have any questions, just unmute your mic and please ask your question.
Just a tiny point, because Tadashi asked about your example of the relation between your, like going back to, can you go back to the slide where you just, he asked?
This one?
Oh yes, that one, yeah. You said density of states rotary equals like a power, but in a black hole, it goes like exponential, right? So.
So that's true. So for example, in string theory, it's known that the density of states diverges as exponential function, and the coefficient in the exponent is the alpha prime. Yeah, that's right. So it's Hagedorn temperature.
So it's just usual. It's not e to the Bekenstein.
Right, and also so here, so suppose I replace this power function by exponential, as you say, then still, where is it? Sorry. The computation, which I showed, this one. So suppose I use the exponential function here, then still we can get the saddle point, which.
Oh yeah. Your computation is totally fine. I'm just saying that because of that. But going back, can you go back?
Yes.
Because of that, your proof that energy goes like a temperature doesn't apply. And in fact, energy goes like a temperature to the dimension of space-time, right? And CFT at the high energies.
Yeah.
So it's just simply your setup is not the last two lines are not the right setup to compare with your, translate your bound to Marasena-Schenker-Stanford setup. That's all I'm saying. Your bound itself is fine. I mean, it's just derived from the conversions. That's fine.
Yeah, I think there is a miscommunication about the definition of this energy. So this energy is a total energy rather than the energy density. So
total energy.
Yeah.
Okay, total energy. Sorry. Okay.
Yeah. So that's why Tadashi actually thought that the volume dependence would be important here. So in higher dimensional system, as you say, the dimension of space is important in the comes into play. But here, since I talked about quantum mechanics, there is no spatial dimension. So the total energy is that's it. But
but you put CFT on some finite space, and then you just heat up, and then it's not just T to D.
Yeah.
T to D, right?
Yeah. So this is always total energy.
Yeah, but still, the volume can be fixed. I mean, when you heat up.
That's right. Then we need to be careful about the scaling. Yes.
But that's consistent because your last line is already violated. It's just E to the.
That's right.
E to the some power. But
yeah.
So that's it. That's just a small comment. Yeah.
Thank you very much.
Okay. Any other question? I think we can have a couple of questions.
So can I ask a question? Yes, thank you very much for very beautiful colloquium. And so in the middle, so you talked about, you have a nice table that the whole different quantum mechanical system has a different feature about chaos. This one, chaos. And maybe for area safety side, maybe we expect both criterion should be satisfied, like spectrum also should be chaotic, and also scrambling should happen. And that case, maybe we choose this middle one, coupled harmonic oscillator, which is much close. Indeed, that's the most, but it's very closest to matrix model, like theory.
Sure. Yeah, that's right. I agree with you, but it's just an expectation. So for example, the computation of out-of-time order correlator for shock waves, it's exponentially growing. So it's following this definition too, and diagnosis comes only from the exponential growth. And normally we usually expected that classically chaotic system will give you the exponential growth of OTOs.
I see.
That's true. But it may happen that, for example, classically integrable system may allow exponential growth in OTOs. Right?
So, but usually in ADS50 we relate this gravity side is very simple classical system, and it's as you nicely showed, it's also related to some inverse harmonic potential like behavior or geometric. And on the other hand, if we take this holography, then we go to quantum many-mode systems, which is really interacting quite a lot, and not just single particles. So in that sense, I find it's very natural that you are this coupled harmonic oscillator.
Sure.
Yeah, sounds like a really nice toy model.
Yeah, I totally agree with you. Yeah, but there still remains a possibility that some classically integrable systems may allow gravity to.
I see.
Too. Yeah.
Yeah. If we that's real gravity dualized, that sounds, I think, very interesting. Yes.
There's certainly sufficient condition, right? Because it's Colloquium theory is a coupled harmonic oscillator. So
yeah, interacting couple. Yeah.
Yes. Can I ask one more question? By the way, talk was great. Thanks. Like you said, classically, you also raise or you showed kind of two way of kind of diagnosing, like a Poincare section and looking at the behavior in a Poincare section. And you also, show like Lyapunov type thing at the classical level. What's the precise relation between these two?
Thank you for the question.
At the classical level.
Yeah, at the classical level, so how to use these two things are kind of different. So if you just want to see whether this system is classically chaotic or not, then normally this Poincare section is an easier way to compute. So we take this thing and plot things, and then, oh, okay, this is classically chaotic. But if you want to know how chaotic this system is, and then label the quantum systems by how much the chaoticity changes for each system, then you need to compute this Lyapunov exponent. And as you can see from this definition, this computation is not so straightforward, in the sense that, for example, this Lyapunov exponent may depend on the initial condition. And so you need to choose numerically many initial conditions, and then compute the Lyapunov exponent for each and take the largest one. So that's the computation of Lyapunov exponent. So numerically, it's cost really high compared to the Poincare section.
Okay, let me be specific. For example, if you look at just the Poincare section, and it looks like chaos, is it possible that this kind of sensitivity to initial condition is not exponential for any quantity or something? That's what I meant by if it's kind of some precise relation between the two.
As my experiments, I have not encountered such an example. And for example, this is the stadium billiard. And if you look really closely, then this is, I would say, scattered plot. But if you look carefully, then there seems to be some vacant area or some regularly seen orbits, something around here. So if you choose the initial condition, for example, around here, then the Lyapunov exponent may be 0. Yeah. So even though you plot this Poincare section, normally it's a mixture of scattered region and regular region. And if you accidentally choose the regular region as a computation of Lyapunov exponent, then it gives you 0. That's why you need to choose many initial conditions to compute the Lyapunov exponent. But yeah, normally if you have a scattered plot, this means that once you go around the phase space, then it goes to very different points, and it goes to again the very different points. So it becomes a scattered plot. So exponential growth may be necessary to have the scattered plot.
Yeah, because I'm asking because I thought that kind of randomness of energy levels are quantum version of the left, and scrambling is a kind of quantum version of the right. But
that's right.
But anyway,
that's right.
Then it's just simply,
Nice. Yeah, I don't know. Thank you for the question. I don't know the pure mathematical relation between these two. Yeah, as an experience, I know that these two are related.
Yeah, related for sure. Yes. But, okay. Thanks.
Thank you.
Okay, I think it's a good time to stop question. So if you have more questions, we are going to have an online coffee time from now on at the spatial chat. You can find the link in the chat box in this Zoom. So if you have time or if you have questions, please join us. So anyway, it was a great talk. So thank you very much, Professor Hashimoto. Let's thank him again.
Thank you very much.
Thank you very much.